Hi guys, so in this video I'll explain how to compute the SVD with an example. And for computing the SVD, I'll be using the Gram Schmidt orthonormalization process, which I've explained in the previous video. So if you don't remember, you can just check it out. But as a quick recap, if I have a matrix with vectors v1, v2, v3, and I want to convert this to an orthonormalized matrix of vectors u1, u2, u3, then I use this formula wk equals vk minus vk is the current in the vector in the current iteration minus sigma of ui is the normalized vector from the previous iteration, dot product with vk, uh, and then multiplied again by the ui, the normalized vector, and from the previous iteration. So when I find wk, so uk for the current iteration will be wk, the value of wk normalized. So you'll understand this better when we do the example. So first, let's compute A transpose. So we need this to compute the U matrix in U sigma and V transpose, right? This is what makes up the SVD. So we need A transpose to get the value of the U matrix. So this is basically 5, 5 minus 1, 7, and 5 minus 1, 5, 7, right? So when you multiply this, the value of A transpose is equal to 50, and 35 minus 5, 30, 30, and wait, hold on, 5, 5, 25, 50. Yeah, 50, correct. So this is the value of A transpose. So now to find the eigenvalues of this vector, we basically have to find the determinant of A transpose minus lambda I and equate this to 0. This will help us get the eigenvalues of A transpose. So so when you calculate this, so A transpose minus lambda I is equal to 50 minus lambda, 30, 30, and then 50 minus lambda, right? The determinant of this is equal to 0. So basically we will get 50 minus lambda the whole square minus 900 equal to 0. So this is equal to 2500 minus 2 minus 100 lambda and plus lambda square minus 900 equals 0. This basically is equal to, simplified, it's lambda square minus 100 lambda plus 1600 equal to 0. So when you factorize this, you get the values of lambda as 80 and 20, right? The thing is, it's very important to make sure that your eigenvalues are in descending order. So we always take the larger eigenvalue first and compute it first, and then we take the smaller eigenvalue, which is 20. So now, if you remember the formula for eigenvalues and eigenvectors, if you perform a transformation on a matrix X, it only scales the matrix X. That's the definition of eigenvalue, right? And this is a formula basically. So if I take this ax minus lambda x, if I take it to the left side, I get 0. This implies that a minus lambda I into x is equal to 0, right? So now my goal is to find the value of this vector x. What is that? I have my eigenvalues. I have the value of a, Now I want to find the vector x. This is basically finding the vector in the null space of this vector, okay? Uh, I have to find some values of x such that this equation is satisfied. So over here, A is basically my A transpose minus lambda I into x equals 0. So first, let me take lambda 1 equal to 80. So I basically have minus 30, 30. I've just put the value 80 over here in lambda. And I have 30 and I have minus 30, right? Into x. Let's take the values of x as some v1, v2. This is the vector. I have to equate this to 0, right? So basically I have two equations. The first one is minus 30 v1 plus 30 v2 is equal to 0, and 30 v1 minus 30 v2 is equal to 0. So this basically gives us, in both these equations, we get the implication that v1 is equal to v2, right? So this basically means that there are an infinite number of solutions for v1 and v2. You can take v1 and v2 to be anything. They will always be the eigen for this matrix. Whatever value you take for v1 and v2, they will always be the eigenvector for this particular eigenvalue 80. So just for simplicity's sake and to make the calculations easier, I'll take v1 is equal to v2 is equal to 1. Okay, this is for the eigenvalue 80, right? Remember this. Okay, so so in the X matrix I have 1 and 1 now. Okay, and I have to find the other two values over here. That I will find using A transpose. Sorry, that I will find using the second eigenvalue. So for the first eigenvalue, I get 1 and 1. So for the second eigenvalue, which is 20, I do the same thing again. It's 50 minus lambda, 30, 30, and 50 minus lambda. This time, if I take lambda to be equal to 20, this gives me 30, 30, 30, and 30, right? Multiply this by v1 and v2, we get 30 v1 plus 30 v2 is equal to 0, and 30 v1 plus 30 v2 is equal to 0. Right? So this is v1 equals minus v2. This implies that v1 is equal to minus v2. So whatever value we take for v1, we have to negate that value, and that is the value for v2. And that is the eigenvector for the eigenvalue equal to 20. Okay, so again, for simplicity's sake, I'll take 1 and minus 1, right? So this is my vector that I have to orthonormalize. Okay, so basically this vector, let's call this vector f, right? This f vector is my f matrix. It's not a vector, it's a matrix. That f matrix is this matrix over here in Gram Schmidt orthonormalization process. So now I have to apply this formula and I have to find the orthonormalized process or orthonormalized vector matrix. Sorry, it's confusing. Orthonormalized matrix for that. So I have my vector 1, 1, 1, and minus 1, and I have to find the orthonormalized matrix for this. So we know the formula is Vk minus sigma I equals 1 to k minus 1 ui Vk is a dot product and into ui, right? So now when k is equal to 1, this entire value will be 0 because k minus 1, so that's 1 minus 1 is equal to 0. So w1 is equal to v1. This is V1, this is V2, right? So for the first iteration, W1 is just equal to 1 comma 1, right? And the value of U1, which is my orthonormalized matrix, U1 and U2, the value of U1 is basically W1 normalized. So that's 1 divided by root 2 and 1 divided by root 2, correct? So that's 1 divided by root 2, 1 divided by root 2. Okay? Uh, okay, I've run out of space. So I'll go on to the next page. So now I found U1. Now I have to find U2, right? How do I find U2? Well, that's W2, right? Because K was 1. So W2 equals V2 minus U1 from the previous iteration. Okay, now it goes from 1 to 2 minus 1, right? Into V2 into U1. Okay, so W2 is equal to V2 is also 1 comma 1 minus U1. U1 is 1 by root 2 comma 1 by root 2. It's dot product with V2, which is 1 comma 1. And then when you do the dot product, you get a scalar quantity. You just multiply it by the vector U1, which is basically, U1 is basically 1 by root 2 and 1 by root 2, right? So when you do this, you get 1 comma 1 minus x to x, y to y. It's a dot product multiplication. So that's, and then you add them. So that's 1 by root 2 into 1 plus 1 by root 2 into 1 multiplied by 1 by root 2 comma 1 by root 2. So that's 2 by root 2, that's root 2. So that's 1 comma 1 minus under root 2 multiplied into 1 by root 2 and okay, I think I made a mistake. Yeah, so V2 is minus 1. It's not 1. V2 over here is minus 1. So I need to change this to minus 1 everywhere. And even this to minus 1. Okay, this is minus 1, which means that this will be subtraction. So that doesn't give us root 2, that actually gives us 0. Okay, that actually gives us 0. And 0 into 1 by root 2 comma 1 by root 2 is just 0. So this tells us that W2 is also equal to 1 comma minus 1 minus 0, which is just equal to 1 comma minus 1. Okay, that's W2. Now U2 is W2 normalized, which is equal to 1 by root 2 comma minus 1 by root 2. That's the value of U2. So U2 is 1 by root 2 comma minus 1 by root 2. This is our U matrix, okay? This is equal to U. So in the SVD formula, you have U sigma V transpose. U is equal to 1 by root 2, 1 by root 2, 1 by root 2, minus 1 by root 2, right? That is the value of U. Now that we found U, we have to find V transpose. Now, just a heads up, sigma over here is just the under root of your eigenvalues, okay? So we have our eigenvalues as 80, and 20. And we know that sigma is a diagonal matrix, right? And the values of sigma are just the square root of the eigenvalues. So this will be 4 root 5, which is square root of 80, and this will be 2 root 5, which will be square root of 20. Okay, that is sigma. So now we have u and we have sigma. Okay, now we have to find v transpose. How do you find v transpose? You basically have to take A transpose A. Okay, when you take this and the entire process that we did for A transpose, you have to do the same process all over again for A transpose A. The matrix that you get in the end will not be U, it will be equal to V. Okay, that's the only difference. Otherwise, the process is exactly the same. So let's do this again. A transpose is 5 minus 1, 5, 7. And A is 5, 5 minus 1, 7, right? So when you multiply it, you will get 25 plus 1, 26. 35, 25, wait, 25 minus 7, so that's 18. And 25. Wait, hold on. I think I did a mistake. 25. No, that's correct. 18. And then 25 minus. Yeah, okay, correct. 18. And 5 5 is 25. Is 25 plus 49. 49, 69, 74. Right? So, yeah, that is A transpose A. Now, again, we have to find the determinant of A transpose A minus lambda I and equate this to 0. This will give us the eigenvalues. So 26 minus lambda, 18, 18, and 74 minus lambda is equal to 0. The determinant of this is equal to 0. Now we already know that the eigenvalues are 80 and 20, so I'm not going to compute it again. But if you want to verify, you can just compute this again, all over again. You will get the eigenvalues as 80 and 20. Just take the determinant, multiply this, subtract them, and you'll get the eigenvalues as 80 and 20. So I leave the thing to you because we've already done this in the previous one, A transpose. The eigenvalues don't change, right? So now I have to find A transpose A minus lambda I into x is equal to 0. So I have to find the vector x in the null space of this one. So let's take 80 first. So 26 minus 80, 18, 18, and 74 minus 80, right? Into V1 and V2 is equal to 0. So this gives us 54 minus 54, 18, 18, and minus 6 into V1 and V2 is equal to 0. So the equations I get are basically minus 54 V1 plus 18 V2 is equal to 0, and plus 18 V1 minus 6 V2 is equal to 0. So basically I basically have the value of V1 as 1 and V2 as 3. Okay, V1 is 1 and V2 is 3. I have to find the other one. So now I have to find the value of this in the for the eigenvalue 20. So I'll do 26 minus 20, 18, 18, and 74 minus 20, right? This is into V1 and V2. So this, if you multiply, you get 6, 6, 18, and 74, 54. Again, you'll get, let's just see, you get 6 V1 plus 18 V2 is equal to 0. So you get 3 and minus 1. Okay, so this is your vector that you have to orthonormalize. Okay, 1, 3, 1, 3, and 3 minus 1. This is a vector that we have to orthonormalize. I'll write down again. 1, 3, 3 minus 1. I have to orthonormalize this vector. So again, W1 is equal to V1. Okay, in the first iteration, W1 is just equal to V1. So U1 is equal to W1 normalized. This is just 1 by under root 10 and 3 by under root 10. Okay, so my orthonormalized vector is 1 by under root 10 and 3 by under root 10. Okay, I have to find the second column of my orthonormalized vector. So that's W2 equals V2 minus U1. This is U1. Dot product of V2 into U1, right? So that's 1 by under root 10 minus 3 by under root 10 minus, sorry, not minus, I'm sorry, this is just a vector. U1 is, sorry, I made a mistake. I'm getting a little, that's the problem with this method. It's very procedural, it's very easy to follow. The only problem is you can make mistakes with V, U, or some addition subtraction. V2 is actually 3 comma minus 1. Okay, this is your V2. V1 and V2, right? So it's 3 comma minus 1 minus U1 is this vector. So 1 by under root 10 comma 3 by under root 10 into V2. V2 is again 3 comma minus 1, and you multiply this into U1, which is 1 by under root 10 and 3 by under root 10. Okay, so this is equal to 3 comma minus 1 minus 3 by under root 10 and minus 1 by under root 10. This again comes out to be 0. Okay, this, if you take the dot product, multiply this with this, multiply this with this, add them, you get 0. So into 1 by under root 10 comma 3 by under root 10. So this entire thing becomes 0. So W2 again in this example is 3 comma minus 1. So U2 is W2 normalized, okay, which is equal to 3 by under root 10 minus 1 by under root 10. Okay, so my U2 is basically 3 by under root 10 and minus 1 by under root 10. Okay, so this is my so wait, I'll just go down and I'll write it. I have no place, never mind. So this is my V vector. My V vector that we just found was 1 by under root 10. Wait, what was it? It was 1, 3, and 3, 1, right? Minus 1. 1 by under root 10, 3 by under root 10, 3 by under root 10 and minus 1 by under root 10, right? We found this. The orthonormalized vector is actually the vector V, but in SVD we have U sigma and V transpose. So you just have to take the transpose of this matrix. So V transpose is basically just switching these two. So 1 by under root 10, 3 by under root 10, 3 by under root 10, and minus 1 by under root 10, right? So in this case, it doesn't change. You have V equal to V transpose in this case, okay? So ultimately, now that we had the A vector A matrix as 5 5 minus 1 7, and we decompose this A matrix into U sigma and V transpose, okay? So U is 1 by under root 2, 1 by under root 2, 1 by under root 2, and minus 1 by under root 2. Sigma is 4 by under root 5, 2 by under root 5, 0, 0, because it's a diagonal matrix. And V transpose is 1 by under root 10, 3 by under root 10, 3 by under root 10, and minus 1 by under root 10. Okay? This is equal to A. This is U sigma and V transpose, and that's how you find the SVD of a matrix. I know it's a little procedural and it's a little long, but I think this is the easiest method to get to the SVD of a matrix, to get the SVD of a matrix using amongst a lot of other methods that exist. Now, as an exercise, what you can do is you can try and verify this in using Python and NumPy. Just multiply these vectors, or sorry, these matrices, U sigma and V transpose, multiply all of them and check if when you multiply them, do you get the same matrix 5, 5, minus 1, and 7? You can take this up as an exercise. I think you will, because if you've done all the steps correctly, you will get it correct. The multiplication will equate to the matrix A. You can use NumPy for it, it's super fast. So that's how you find the SVD. That's how you compute the SVD by hand. Now, if you have any questions, just leave them down in the comments and I'll answer them. All right.